Hello everyone, and welcome to the Week 7 video for COMP3141. So today we're going to be talking about a set of type classes, some of which you've seen before and some of which you haven't, which all generalize over higher kinded types, and that means types that have a kind that are other than star. So we've already seen functors as an example of such a type class, and we'll briefly go over those again. And we've even seen monads, although I haven't explained to you yet what monads actually are and how they actually work. We've just used a few examples of them with respect to I/O and state, which are what we used last week. So in this lecture, what I'm going to do is introduce or reintroduce all three of these type classes, the functor type class, the applicative type class, and the monad type class, and tell you how they relate to each other and how we can use them to accomplish various tasks. So they are very commonly used abstractions in functional programming. For example, monads are almost ubiquitous in Haskell, but also in other programming languages, even imperative programming languages. Things like monads and functors have become increasingly common, and you can find them in lots of different places. In particular, with the advent of concurrent programming in mainstream programming languages, the use of futures and asynchronous and await statements and things like that end up taking on a very monadic structure. So we'll be talking about what they are, but unlike many of those other programming languages where these concepts are used, in Haskell these are proper type classes. They're not just design patterns or general tendencies or styles of designing an object. So in Haskell these are not just stylistic choices or design choices, but rather actual features of the programming language and its standard library. So let's just remember from a few weeks ago when we introduced kinds. So kinds are essentially like the type system of the type system. So a type like int will have a kind like star. So star is the basic kind, and that just means the kind of types that have values. So int and bool and maybe bool, all of these things have kind star. And maybe is parameterized by an argument, so it is almost, you can think of it maybe just by itself without an argument, is a function from something of kind star to something of kind star. So if I give it an int, it will give me a maybe int, which is a new type of kind star. So we've also seen this type state last week, which was for these stateful computations. And it took in two parameters, right? The first parameter was the type of the state. So that type's kind is star. And then the second parameter was the kind of the, or the type of the return value. So its kind would also be star because they're both types that can have values. And so therefore state overall is of kind star for the state, and then to star for the return value, to star, which is its ultimate return type. So star to star to star would be the kind of state. So we've seen this functor type class, which has a single method called fmap, which looks a lot like the map function that we've seen for lists, and these two laws, right? And we've seen instances for lists, maybe, tuples, and functions. If you don't remember the ones for tuples and functions, the tuples, one will work on the right-hand element of the tuple and leave the left-hand element untouched. And we'll get to that in a moment. And functions will do function composition, right? We also have instances for I/O. So we've seen I/O computations last week and state. And for both of these, we can write an instance, and I'll show you what it looks like. let's go to a terminal. So let's just open up a Scratch file. So here we're going to implement an IO map function, which is a function. Let me make that a bit bigger. There we go. An IO map function, which is a function that, given a function a to b, will take an IO of a and give me an IO of b, right? So it looks a lot like list map, but it's for an IO computation. And so this is taking the function f and my action a, or let's not call it, let action act. And what I need to return now is a IO action that returns a b. So I'll use my do notation, and I will first run the action to get the a out of it, and then apply the function f to that a, and then wrap it up again in IO to return it, right? And that is essentially the fmap implementation for IO, right? So it will run the procedure and then run this pure function a to b on the result of that procedure once the procedure has finished, right? And it composes basically this IO procedure with this function to give you an IO procedure that returns the b instead of the a. So that's map for IO, and we can even have the same thing for state. For any state, we can just say state map a to b, state s a, state s b, and the code is exactly the same. So we can see here that we have the same code because all of these things just rely on the bind operation and the pure operation. So this is in fact the interface of Monad, which is what we saw last week. We could even have a more general function called monad map, monad m, that just runs on any monad m, like this, monad map, and monad map would do just as well as IO map or state map would, right? We could just use this for both of those. So we can generalize over the concept of a monad and not have to write an individual function that works on state and works on IO and works on every other type of monad that exists. But in the way the Haskell standard library sets this up, it actually this is putting the cart before the horse, because Haskell standard library sets up monads to require a functor instance. So functor actually comes first, monad comes later. But we'll get to that. So it's possible to define these instances. We have functor for lists, maybe, tuples, functions, IO, state, and also gen. So if you've seen gen before, but I would forgive you if you don't remember, because every time we've shown you gen so far, it's been, don't worry about this for now, we'll show you what it means later. So gen is the type of a quick check generator, right? So in quick check, whenever you have an instance of arbitrary, I'll just write out the code here, class arbitrary a, where it has an method called lowercase arbitrary, which is a generator of a's, and then it also has a shrink function, which given a failing a will give you several more candidates that maybe could be used for testing. And shrink is optional, you don't need to implement it, but arbitrary is mandatory. So what is a gen? Well, it's essentially a random number or a random element generator, a random arbitrary value generator of a's, right? So gen of a is equivalent to a random generator of a, of type A. So it will just produce values of type A. Let me actually say random generator of values of type A. So the useful thing about fmap here is that I can run functions on the results that I generate, right? So for example, an easy way, and this is in fact the way we do sorted list generators, is if I wanted to write a generator for sorted lists, which is a generator of A where A satisfies ORed, right? So this is in here. Then to produce a sorted list of A's, all I need to do is first get a generator for A's. So I need A to be an instance of arbitrary. And then I can say arbitrary. And using that, it will be of type gen of A, right? And then applying my fmap function, remember fmap, I can sort it. Sorry, I need to get a list of these. My mistake. I need to first generate a list, which I believe there's a function in quick check. Let me just look it up. I can never remember the names of these things. Test.quickcheck, here we go. I always have to look it up because it's it seems to change every so often, and I always get it mixed up. Right, so there's a function, and if you Google, you'll find it, called listOf, which, given a generator of A's, will give me a generator of lists of those A's, right? So if I want to generate my sorted lists, I can fmap sort on a list of arbitrary A's, right? And I know I can create arbitrary A's because I have this arbitrary A constraint. And so this is a generator of lists of A's. So what we've done here is first we just generate any arbitrary list of arbitrary elements, and then we sort it. And then by applying the sort function to the result of the generator using fmap, we can produce a generator for sorted lists. So this is essentially the trick that we want to use with functors. Whenever we have a type that instantiates functor, it usually contains some value or produces some value, right? So generators here I would say they produce values of type list of A here. Whereas other examples of functors, like maybe, they sort of contain, or maybe don't, but they maybe contain a value of a type A. Lists contain a value of type A, right? So they either contain or produce a value. And what the fmap function does is apply a pure function to all of the values that the structure either contains or produces. So if it contains it, then it just applies it in place. And if it produces it, then it sort of saves that function to be applied whenever the structure produces a value. So our generator here produces a value, and then this sort function is applied to it. That's what fmap does here. So that's the intuition behind functor. And we've seen these functor laws, and all they say is that if I apply the identity function to every value that's produced or contained within a structure, then that's the same as not changing the structure at all, right? And also, if I apply a function g to everything inside the structure, and then I apply the function f to everything inside the structure, then I get the composition of those two. It's the same as applying the composition of those two to everything inside the structure, right? So that's functor. Hopefully we all remember functor. So I have a slide about gen, but essentially it's just saying what I was saying in the editor before. Okay, so that's functor. So now let's talk about a slightly more interesting type class. Let's suppose that I have two functions here. One is given a student's name will maybe give me a ZID, and another one given a student's program will name will maybe give me which program they're enrolled in. So we can actually go ahead and implement this in our Scratch file. Let's just make some space. So we'll have lookup ID. If their name is Liam, then their ZID is just, and here's my ZID. And if their name is unlucky, then they can have a very unlucky student number. and if they are prosperous, they can have a very lucky student number, and otherwise we don't know who they are, we don't know their student number, right? So this is just a simple silly example. So we have our lookup ID function here, which is of type name to maybe ZID, where name is just a string and ZID is an int. And we also have a data type for the program that they're enrolled in, so maybe COMP.Sci or software engineering, or I don't know what COMP.Sci actually is, but whatever. Or bioinformatics, or anything else. Maybe it's just comp. I think it's just comp. Computer engineering, and that'll do, right? And we'll say that if you look up the program, name to maybe program, we'll have a similar sort of situation here. I was a COMP.Sci student years ago. We'll say unlucky here is a software engineering student, and prosperous here is the computer engineering student, and no one does bioinformatics. So there we go. Oops, now I've made a typo here. I should have put a just constructor on all of these because this is returning a maybe. So there we go. Here's our two functions that return maybes. And now what we want to do is let's suppose we have some sort of function, make record, that given a ZID and a program will give me a student record. I'll just define what that is and add some derived instances to program here. Let's just say a student record is just a tuple containing the ZID and student record. ZID and student records, ZID and program, of course. Okay, so our make record function will take those two arguments. Now remember, and we'll ZID and program, and it'll just put them in the tuple. Now, what we want to do is create, like, let's say we are trying to make a record for me. So then what we'd do is look up my name using the lookup ID function, and that would give me a maybe ZID, right? And then I'd look up my name using lookup program function, and I'd get maybe program. So I have, let's just write an example. Liam is a student record. Liam is, firstly, we go let the name be, or the ZID, maybe ZID, be lookup ID of me. So MZID here would be maybe ZID, and then we have maybe the program. And then what I want to do is call the make record function on this and this. But if I did that directly, it would not work, it would not compile. And I can demonstrate that. I will have to comment this out because I didn't import quick check, but that's okay. There we go. Now let's go stack REPL load scratch. Yeah, so it says I expected a program and you gave me a maybe program, right? We haven't accounted for the possibility that maybe these lookups failed. Now, of course, I know that this will succeed because I know that I'm in this list, but if I had maybe mistyped my name, then this would cause a problem. So what we really would like to do is return maybe student record and only return just the actual record if we have both the ZID and the program. And if we don't, we want to just sort of return nothing and give up. And preferably, we'd like to give up straight away, right? As soon as one of these things fails, we just want to give up the whole thing. We don't want to have to compute more things afterwards for no reason. So let's say, so what we really want to do is have a function that takes in, so we'll have a function which I'll just call, actually, what did I call it in my slides? Let me just find out. Right. It's sort of like maybe map, right? It's sort of like map, except, or fmap for maybes. So if you remember, fmap is of type A to B to maybe A to maybe B. But what we want here is for our maybe map2 to take in 2 arguments, right? So make record only takes in 2 arguments, so this function type doesn't quite cut it. If I applied fmap to make record, I would get a function. It would make record of sorry, if I applied fmap to make record, then it would give me a function from maybe ZID to maybe of a function from program to student record, which isn't quite what I want. So what I really want is something like this, right? Maybe A to maybe B to maybe C. So it kind of looks like fmap, but with an extra parameter. So so we have an argument here, which is the second one. And then if I had such a function, we could even implement it, right? So maybe map2 f, well, my f takes in 2 parameters now. So here I have the maybe, so if the first one is nothing, then I just want to abort and return nothing. And if the second one is nothing, then I want to abort and return nothing. And otherwise, they must both be just. So we have a just A and a just B, and then I'll apply F2, F2 A and B, and wrap that up in a just. Right, so this would be the implementation of maybe map2. But then imagine that I also had to include an extra element in my student record. Suppose I also included the actual name, the original name. And my make record function, let's just put the name here. Just arbitrary order, it doesn't really matter. But the name actually goes there. Okay, so now we have an extra argument, and now this maybe map2 function isn't good enough. Now I need a maybe map3. This is pretty unsatisfying, right? If we had to write a function for every single possible combination, every single possible number of arguments, we'd have a lot of functions to write. Right? And they grow bigger with each iteration. So this is no good. We want something a bit more general than that. But I mean, if we had maybe map3, we could do something like make record, yeah. First we need the ZID, then we need the program, then we need the name. Now the name is already pure, so I'll wrap it up in a just, right? And then that way it will be passed in. So maybe map3 expects 3 maybes, but this last one is not actually a maybe, so I'm just wrapping it up in just to fit the type. So there's my function, but it's not ideal because I keep having to generate these new functions each time for different numbers of parameters. So what can I do instead? So I'll go back to the slides. Yeah, so if we made maybe map2, we might need maybe map3 or maybe map4 or whatever, just depending on however many parameters we have. So this is pretty bad. So we'll return to fmap and see what we get when we just try applying fmap with make record. So this is just with the 2 argument version. So So if I apply fmap to make record and then pass in my ZID, or maybe ZID, then fmap will return maybe a function from program to student record, right? Remember that Haskell functions take in a parameter and then return a new function if they take more than one argument, right? So this is the return value of make record. If we look at the type of make record, given the ZID, it will return a function from program to student record. So given a fmap of make record is given a maybe of ZID, returns a maybe of the function program to student record, right? So that's what lookup record prime does. Just given the name, it will just provide the ZID to fmap make record and then give me a maybe wrapped function. Now that's a bit of a weird thing. Why would we want a function inside a maybe? Well, what we have now is a function that accepts a program inside a maybe, so it's a maybe wrapped function that accepts a program, and we also have program, which is a maybe wrapped program, right? So it's a maybe program. So we have the function and its argument both inside a maybe. And what we want to do is apply that function to that argument if both of these maybes are actually justs, right? And if either of them are nothing, we want to abort. So this pattern is what is captured by the applicative type class. That's why it's called applicative, because we want to take the functions inside the structure and apply them to their arguments. And the motivation for it is to essentially do fmap, but for more than one argument functions, right? Yes, my computer's making some noise. Sorry about that. Okay. So let's assume that we have, instead of maybe map and all of that, let's give ourselves, we've got ourselves fmap. We know we have fmap because maybe is an instance of functor. So we've got fmap here already, right? We know that exists. Now what we want to do is define this special function, which I'll call apply. And what it does is take a maybe wrapped function, a to b, and a maybe of its argument, and gives me a maybe of its result. So you can see it actually looks quite a lot like fmap, right? If I line it up like that, it's very similar. The only difference is the function is also inside a maybe. So if I have this apply function, and I say, okay, if any of them are nothing, then straight away we give up, right? We don't care if any of these things have failed, we just will drop everything and return nothing. Otherwise, I will have just f and just my argument, and I will just return just of f applied to the argument, right? So it's essentially wrapping up function application inside a maybe. So with apply, then instead of maybe map 3 here, I can go make record. So apply well, firstly fmap make record on mzid. Remember that this is of type maybe the rest of this, right? So make record takes in a ZID first, so we fmap make record on mzid, and it gives me this maybe function. And then if I apply, using my apply function, that to mprg, and then apply that to just Liam, then it will give me my result, and I can even test it out. So Liam is nothing, and the reason it's nothing is because I made a typo. If I change my name to be correctly spelled, then it gives me my student record, right? So what this is doing is effectively making it sort of act like exceptions. The moment any of these computations returns nothing, we just give up. And this is a lot briefer than pattern matching on each of these maybe arguments. If I had to do case mzid of just something or nothing, and if it's nothing, return nothing, and then do another case inside, and then another case and another case for every single maybe that I have, it would be very verbose and ugly. So this is why we have these convenient type classes. So now, all of these examples just use maybe, but functor is much more general than maybe, and applicative is also much more general than maybe. It applies to many, many different types of structures. So what the applicative type class actually is this. It has to be a functor already, so we have to have fmap, but we also get pure, which we've seen before, right? We've seen it with IO and state. So you were using applicatives without realizing it when you use this pure function, and star, or the app operator it's sometimes called, which was my apply function here, right? So it takes in the f, the maybe, for example, of a to b, and then the maybe, for example, of a, and then returns the maybe, for example, of b. So it applies the function that is wrapped up inside the structure of instance, which is an instance of the type class applicative. So if I were to rewrite this using the actual applicative operators rather than my apply function, then this would be fmap make record mzid applied to mpig, right? And then apply that using the app operator to just Liam, and just here is pure, right? Pure is the function, right? Remember, it takes in a and gives me an f of a. In this case, it would be maybe of a. So the obvious implementation of pure here is just. But now this is generic across any applicative type class. If I remove, if all of these were, so this expression here works regardless of whether it's a maybe or a list or anything else. So, cool. We can also write equivalently. It's exactly the same thing. Instead of fmap, right? So we have fmap here. We also have our apply function, which I'll just line up again. You might think that, well, if we look at the type of pure in this context, it is a to maybe b, or a to maybe a. So what I could do is, instead of applying fmap, I could use apply and pure. So I can go pure of make record, and that would give me a maybe wrapped function, right? I'd wrap up the function make record in a maybe, and then use the application operator to apply that to mzid. And in fact, that's always the case. We should always, it's part of the laws, we should always be able to implement fmap f of x as pure f applied using the application operator to x. Okay? So in general, whenever we have an n-ary function that we want to apply to several arguments, then inside the context of one of these functors, then we use pure and then star to separate all the arguments, right? So I have a schema here. And this takes a regular function application and sort of lifts it up into the maybe or whatever other applicative functor you want realm, right? So we can apply this function that is now operating on maybe arguments rather than just plain arguments. Okay. So what we'll do is a short proof, because I want you to this will help you to get a handle on the applicative laws, because there are 4 laws for the applicative type class, and they can be a little bit tricky. So here they are. Now, I would never expect you to memorize any of these, so don't try to commit them to memory. but there's a bit of an intuition behind each of them. So the first one is similar to the identity law of functors. It says if we apply ID, we get the same thing back. The second one is if we wrap up a function f in our applicative functor and then apply it to an argument, which is also just a pure thing wrapped up in the applicative functor, then that's the same as wrapping up the application of that function to that argument. Interchange says that, well, it's a little bit tricky, but essentially what it's saying is if you have a wrapped function and you apply it to a pure argument, then it's like applying the application operator with that pure argument to the wrapped function, right? It's just basically reordering the execution of the effects, if you like, of the applicative. It's a little complicated, but it's a law that you need in order to prevent order dependency in the application operator. Composition is once again quite similar to the composition operator, or the composition rule for functor, right? So it's saying that if you have composition and you apply it to you compose u and v and then apply it to w, that's the same as u of v applied to w, right? So it's essentially the composition rule, but written in a little bit of a strange way. Okay, so let's prove using these four laws that the functor laws hold if we implement fmap using this pure f star x implementation. So let's get rid of these. So let's first remember our functor laws. We have fmap of id equals id. And I'm going to expand this so we get fmap of id x equals x. Right? This is the same thing, it's just giving me an x there. So that's the first functor law. And the second functor law is fmap of f applied to fmap of g of x. Once again, I'm eta expanding here. Is fmap of f composed with g applied to x. Okay, so now our implementation of fmap is this pure f star x thing. So what we want to do is prove that these two laws hold. The first one, well, if I expand the definition of fmap here, I get pure id star x equals x. Well, which of our laws can help us with that? Oh, well, that's just the identity law straight away. So this is true by identity law. So that one's very easy, but the next one's a little trickier. We have fmap of f applied to fmap of g of x. Oops. And we want to show that that's equal to fmap of f dot g of x. Now, let's expand the definition. We get pure f star pure g star x, like that. And then we want to show that that's pure f dot g star x. So this is a little tricky, and I'll just put this down below because we're not there yet. We've got to do some reasoning. So what do we do with this? This is a bit hard to deal with. If I look at my rules, I have only got one option here. I have these annoying parentheses on the right hand side, and the only rule that has parentheses on the right hand side of the app operator like this is composition. On the right hand side of composition here, it looks like what I want. So I'll change the right hand side to the left hand side, and I get pure dot applied to, now my u from the rule is pure f here, my v from the rule is pure g, and my w from the rule is x. And now we don't have any of these annoying parentheses, and the app operator here is left associative, so it's like function application. So now what we want to do is somehow massage this into this. So we see we've got pure, pure, pure. And if I look at my rules, there is a rule that deals with if I've got lots of pure involved. Pure f applied to pure of x is just pure f of x. And here we've got pure of the composition operator applied to pure of f. So that sounds good. We've got pure of, then composition operator applied to f, applied to pure of g, oops, keeps doing that, applied to x. And we can use that, so this was composition in reverse. This is homomorphism. And we can use homomorphism again, and we get pure of dot fg, which is just f dot g, x. Oh, hey, that's what we wanted, right? So we use homomorphism twice. Okay, so that's the proof that the functor laws are obeyed by any law-abiding instance of applicative by implementing fmap this way, right? Okay, good. So let's look at some other instances of applicative. We have an instance for lists as well. So if we look at the type of the app operator applied to lists, we have a list of functions from A to B and a list of arguments, A, and we need to get a list of results, B. So there's two ways we could accomplish this. One, we could sort of pairwise match up each of the functions with one of the arguments, right? So each function gets one of the arguments in the other list, and we just take the minimum length of the two lists. So this is essentially like the zip width function, right? So if I show you the zip width function, just go to GHCI, zip width, if I look at the type, it takes in a binary function here, but essentially, if I take zip width of the application operator, then it is taking in a list of functions, and for each of those functions, it'll apply its argument. So I could go zip width $ operator, and then let's pass in sine, cosine, and tan, and we'll just pass in some random arguments. We have 0, pi, and minus pi. Let's try that. So we get sine applied to 0, cosine applied to pi, and tan applied to minus pi. It didn't seem to... Let's try. And let's just muck around a bit and see what we can do. So what's going on here is we are essentially moving or applying each one of these functions, sine, cosine, and tan, to each one of these, or to one of these arguments. But there's another way we could implement this. We could also say apply sine to all three of these arguments, and then concatenate that to cosine applied to all three of these arguments. And that's sort of like if I did concat map. Would that be like it? No, not quite. That's not quite what I meant. Is it? Yeah, I'll implement that later. But essentially, there are two ways we could do this, and both of these would obey the applicative laws. So the first one is apply. Oh, so the second one in the list is to apply each function to the corresponding value in the list of arguments, which is this zip example that I just showed you. And the other way would be to apply each of the functions in here in my given list of functions to each of the arguments, so all of the arguments, and concatenate them all together. And depending on which way you implement it, you get different results. So let's actually do it. Hold on. Okay, so right, sorry, I was momentarily distracted. We have to implement apply for lists. So there's two ways we can do this: A to B, list of A, list of B. So we could go apply lists of f, f's, x, x's, and just have f of x and then apply lists f's, x's, right? So this is the zip style implementation. Oh, actually, we should be careful here and handle the base case properly. So that's the zip style, which I'll mark with a Z. And the other one is the combinatorial sort of thing, so I'll call it C. And it takes in it's the same type, but what it does is apply f to every single one of the arguments and then concatenate that to applying the rest of the functions to all of those arguments, right? And then when we run out of functions, we just return the empty list. So these give very different results. If I go apply lists Z, then my sine, cosine, and tan, for example, of 0, pi, and 2 pi, 2 times pi, or whatever. Let's, if I swap these around. Right, so we get some interesting things going on here. But it's one function for one argument. If I go apply list C, it's applying all three functions to all three arguments, right? So first it's all of the sine functions, and then it's all of the tan, and then it's all of the cosine. So this is essentially the difference between these two approaches. Now, in order to obey the laws, we also have to provide pure implementations here. And I'm not calling these app and pure because I'm not, so this is pure for the zip one. It's going to take an A and give me a list of A's, because these are already implemented in the standard library, so I'm just using my own names here. So I've got my A here, and I'm going to have to return a list of A's, and also one for the combinatorial version. So the obvious answer to pure Z here would be if I just said, okay, well, just return a list containing A, right? Just make a singleton list that contains an A. But this would not obey the type class laws, because if I look at my laws, let's go back to our laws, it says that if you, for example, apply pure ID to any list, right? In this case, it would be any list V, you should just get back the list V. But if you apply the list containing just ID, so if I show you, in this case, if I were to go apply lists Z, the pure Z of F, or of ID, it would not be the same. It would not be the same as V. Why not? Because let's expand the definitions. Lists Z of lists of ID V. Well, if I look at this, it's going to be, that's the same thing as id empty list v. And let's suppose that v just has like a few elements in it, at least 3, for example, just as an example. v1, v2, v3, let's say. Then if I expand this using the first equation of apply list z, I will get empty list here, and then id applied to f or v1. Okay. Sorry. It would be id applied to v1, followed by apply list z empty list v2 v3 empty list, right, like that. And then if I evaluate id, that's just v1, and then apply list z of empty list is just empty list, which means that I end up with v1 like this. So I dropped the last 2 elements of the second list. So this is not the same as not doing anything. So what I need to do in order to make pure z work with the applicative laws is to provide a list that will have as many functions as there are elements, at least as many functions as there are elements in any list. And the only way to do that is to have an infinite amount of functions. So my pure implementation here actually has to have a followed by pure z of a. It needs to be an infinite list of a's. So this is a bit tricky, right? As opposed to pure c just needs to be a singleton list, and that's fine for pure c. Because my apply list c will obey the functor laws and the applicative laws if I use pure c. So this is the difference between these 2 implementations. Okay. So in the Haskell standard library, the default applicative instance for lists is the combinatorial one, not the zip one with the infinite list. That one is in the standard library, but it's behind a new type. We've seen the use of new types before to give different type class instances. There is one for lists that does this for applicative in Haskell called zip list, but typically the applicative instance that is most commonly used is the combinatorial one. So there are many other instances of applicative. Quick check generators are also applicatives. So if you remember from, I think it was Wednesday of week 4, or maybe it was, I think so. Curtis went through this concrete editor example where we had 2 lists of, well, 2 strings, one for the left-hand side of the cursor and one for the right-hand side. And this left-hand side and right-hand side strings were arbitrary strings in the quick check instance, in the arbitrary instance. So the arbitrary instance for this whole concrete editor would take an arbitrary string and another arbitrary string, right? So these are both generators of strings, and compose and apply that function c, which takes 2 strings and gives me back a concrete, to arbitrary and to arbitrary. So this $ operator here, if I go back, I think I skipped over this before. The $ operator here is equivalent to writing pure f star of this, or similarly fmap. It's the same thing as fmap. So we can say f applied to all of these arguments, right? And that's what the $ operator helps us do. It's rather than write pure f star ma star mb star mc and so on, right? So the first one, if you've got a pure thing on the left-hand side, you can use $ here. You don't need to use pure and star. So anyway, we can basically apply this function c, which takes 2 strings, to 2 generators of strings and get back a generator of concretes, right? That's the use of applicative here. Functions are also instances of applicative in the same way that they are instances of functor. So let's take a look at that as well. So the instances, let's remember the type class for applicative. It is class functor f applicative f, where, and then pure takes an a, gives me an f of a, and star takes a f of a to b, an f of a, and gives me an f of b. So let's keep that in mind. What we're going to do here is implement it for functions. Well, it's already been implemented for functions in the standard library, but I'll just write it out here and then comment it out so that it doesn't break anything. So we have, we already have an instance of functor for functions, which is just function composition. So let's do the applicative one. So let's go applicative arrow applied to with x, where. So arrow takes two parameters, so I provide one of them to be arbitrary x, and that's just and that gives me a star to star kind, which I can define applicative for. So then I have pure of a, and now my f here is arrow x, so it's going to be arrow x a, which is the same thing as a to x to a. Okay, and then we also have star, which is arrow of x and a to b, and we'll expand what that is in a moment, to arrow of x and a to arrow of x and b. Now I know that looks complicated, so let's tease out what that actually means, and we'll implement these in a moment. We have, so that's the same thing. I'll leave it up, but it's the same thing as writing x to a to b, right? And this is the same thing as x to a, and this is x to b. Now this is actually a very important type. It's in computer science theory, this is known as the K combinator, and it's a part of a computational calculus called the SKI calculus. So if you've heard of that kind of stuff before, in theory of computation or what have you, this is closely related. In any event, we have our x to a to b function, and our x to a function, and we have an x, and we need to return a b. So we need xab is the only thing that can return us a b, and it first requires an x and requires an a. The x I can provide by providing the x directly, and the a I have to use the x to a function and provide the x there. Right? So that's what that's doing. And pure has an a and an x and it needs to return an a, and we just ignore the x and return the a. Right? So the SKI calculus, essentially what it allows us to do is hide the presence of a particular argument to many functions. So for example, if you ever have a situation where you've got a function f and it's applied to g of x and h of x and I of x, right? Then what we can do is use our applicative operations here to essentially g h I, and then just apply that all to x. So what this lets you do is essentially hide a given parameter and just describe a computation in terms of and compose a computation together and then apply that given parameter at the end. Now this is actually quite useful. So for example, if you had a type of predicates, right? Let's say a type of a predicate this one, no, that one doesn't actually work. Forget that example. I'll come up with a good example and type it up later. But suffice to say, this is actually quite a useful idiom in functional programming. you'll often find this comes up quite a lot, and it can be very useful sometimes to abstract that into only having one point where you provide the argument at the end, after you've constructed all of your computation and wired it all together. In any event, let's move on. So we have also got instances for tuples. So for functor, let's do the instances for tuples again. This has to be commented out. So we had an instance for functor for tuples, where the first side of the tuple was fixed, and the way that looked was we have a to b to tuple of x and a, right? So xa to xb, right? And f map of f here takes my x and a and just gives me the x again, and then f of a. And this will, what this lets us do is sort of in the opposite sense to the function where it hides a parameter, this hides an output, right? I can apply this f to a particular element, and then the output element, the extra output element x, is sort of implicitly just carried along. So how do we do this for applicative? Let's look at applicative. We're going to need pure, which in this case is going to take an a and give me an x and a. And we need a star, which is going to take in an x of an a to b and an x of x and an a and an x of an n to b. Right, so the x and a bit is the applicative functor here. Okay, so let's just try and think about how we'll implement this. If I look at my instance here, well, I've got an a, but I need to return a tuple of an x and an a. So I don't know what I'm going to return for the left-hand side. So we can't actually implement applicative for tuples, even though we could implement it for functor, without adding an extra constraint. And in the Haskell standard library, the extra constraint that it adds is that x must be a monoid. Now we remember monoids from earlier, I hope. They are essentially the type of the class of types that can be combined and that have an identity element. So now, if we know that x is a monoid, we can pick the identity element as the element we should put in for the x in our pure instance. And then in our implementation of an application, we have an initial x that came with the function, and we have an x that also came with its argument. And what we want to do is return an x that, and as well as the function applied to the argument. And which x should we return? Well, we've got an x and we've got an x prime. We'll use the monoid instance again to combine the two. And that's effectively the way we implement applicative. So what this lets you do, you can imagine that if you had a function that logged certain bits of information. So for example, if I had a function f that took in an a and then gave me a log as well as b, and g also took in x and gave me a log and returned a y, and I wanted to combine both of these using a special function combine that took in my b and a y and gave me a combination z. Right, these are just arbitrary types, of course, and I don't know what the implementation would be, but anyway, then what I can do is I can use my if I use my instance here, I can say combine applied using the fmap operator to f. That's going to give me f of my a. Let's say I have an a, and x is of type x, and then star of g of x, and it will give me this is going to be of type log z, right? So what it does is we have this function a that takes in an a and returns a b as well as a log, but we hide the log here, and g takes in an x and returns a y as well as a log, but we hide the log there, and the combine function takes those two elements and puts them together into a z. And for both of these arguments, when they produce their logs, we just combine them silently using the monoid concatenation operator here, this angle-angle operator. We combine them together and return the log of both of those functions together. So essentially, what's going on here is we have produced a log for each of these functions, and we combine those logs as we move along. And we no longer need to do this manually. We can just sort of thread this extra return value through by using the applicative functor, right? So it's a useful abstraction. So IO and state are also instances of applicative functor. So I'll show you the instances for those as well. So this is all a comment because none of this will compile because it's all in the standard library already. But if I go applicative for IO, let's say, just because it's shorter to type, you can do the same thing for state. A to IOA, well, that's pure, like we've already seen pure, right? So I'm not going to show you how IO is internally implemented, but we know that we have implemented pure before. And for star, how do we implement star for IO? So I've got an IO of a function, an IO procedure that returns a function a to b, and an IO procedure of an a, and gives me, I want to return an IO procedure that returns a b. So I've got my function star a. So I'll call it procedure of a function, procedure of a. Then I will first run the procedure of the function to get the function out. Then I will run the procedure of the argument to get the argument out. And then I will return the function and the argument, applied to the argument, right? So this implementation works for any monad, not just IO, but it shows that every monad is also an applicative functor. But once again, like I said before, this is putting the cart before the horse, because in order to define a monad in Haskell, you first need to make it an instance of applicative. Okay. So that's applicative functors. Now, I appreciate that applicative functors can be quite unintuitive at first, but the intuition that I want you to think about when you're trying to think about applicative functors is that they are essentially like functors, regular functors that just have a map function, but they allow that function to be either over 0 arguments in the case of pure, or more than 1 argument in the case of the apply operator. So essentially what this allows you to do is generalize fmap to work for n-ary functions, for functions that take any number of arguments. That's essentially what applicative functors are. And we've seen many instances, some straightforward and some more confusing, of applicative here. Some of them are very useful, some of them don't show up all that often. For example, the zip list operator, the zip list version of applicative is not very common, but the combinatorial one is extremely common. Okay, so let's move on to monads, and once we've done with monads, I will show you a bunch of examples that will hopefully illuminate more of this for you. Okay. Yeah. So, functors are types for containers where we can map pure functions on them. Applicative functors are types where we can combine n containers with an n-ary function, right? So, functors are exactly 1. Applicative functors are 0 or more for any number of containers. And the last one is called a monad, and monads are essentially like functors and applicative functors, but they allow us to sequentially compose functions that are of the form a to m of b, or f of b in the case of a functor. So whereas applicative functors and functors here both only allow you to apply like a pure function to the results of your I/O procedures, let's say, monads allow us to create a new, or to choose a new I/O procedure, for example, to run after one previous I/O procedure has finished executing. So it allows us to not just run pure functions on the results of a I/O procedure, for example. It would allow us to take two I/O procedures and run them one after the other, where the results of the first one are used to construct the second one. So let's show you a few examples. Monad basically just gives you this extra method here, which we've seen before. It's called bind, right? It takes an M of A in general. It's an M. This could be maybe, it could be lists, it could be I/O, it could be state of A, and then a function that, based on the result of the first computation or container or what have you, it will choose the next computation to run, and then generate, and then it will combine this first computation and the function that then chooses a next computation and that next computation into one overall computation that returns a B, right? So that's the that's the bind method, and there's plenty of instances. So we've seen instances for I/O and for state already. We've used them many times, but now I'm going to implement it for other types. So we have, let's do bind for maybe, which is going to be maybe of A to maybe of B. So I have a computation, you can think of this as, I have a computation that maybe fails, but otherwise will return an A. And then based on that result, if the first one succeeds, I'm going to do another computation that maybe fails and otherwise returns a B. And then I'll put those two things together to give myself a computation that maybe fails or maybe returns a B, right? So you can think of even maybe as like a computation, like I/O or state. So if I go nothing of F, then I give up straight away. That's the typical thing with maybe. And if I have just an A and then F, then I go F of A. And I don't wrap it in just because F here returns a maybe already. So that's the instance of monad for maybe. And there's also an instance of monad for lists. So if I have a list of A's, and then for each of those A's I can give you a list of B's, then I want to return a list of B's. Well, this is actually a lot like, if I just put this in the comment, if I look up the type of concat map, ignoring that it's foldable here, that should treat that as a list, then we have A to a list of B's, list of A to list of B. Well, that's just, if I flip concat map, that's exactly the type that I want. So let's just do concat map here. In many other languages, this is called flat map. So if you ever see flat map or concat map in another language, then what you are doing is using a monadic computation. So we have our list here of A's and our function F, and I'm just going to concat map F onto the list of A's. Okay. All right. So that's the instance for lists. We also have an instance for functors. For functions. So this one gets a little complicated again. Remember, what we're going to do is, the type in general of bind is M of A to M of B to M of B, and here M is going to be a function from some concrete type X, or arbitrary type X. So I'll rewrite the type signature again. We get X to A is the first one, and then based on that we get A to X to B to X to B. Let's implement it. We get the X to A AXB, X. And how do we return a B? Well, we need to use AXB for that. How do we get an A? We use X of A. How do we get the X? We use X, X, like that, right? And so all I did was guide myself by the types there, and I get my implementation. Now this is actually very useful if you have a situation where you want to apply, if you have some implicit state or some configuration. Say I had some global configuration and it was a data type, and I wanted, all of my functions needed to know what the configuration was in order to do anything. Then if I just use this monad instance, I can call all of these, even use the do notation to call all of these functions and not pass the config in. I can just ignore that part. Let's say A to config to B, right? So config is always the last one, and X to config to Y, and what have you, or even B to config to C. Let's suppose I have this, and then I want to write a function that combines that, like, given an A, an X, and a B, given an A and an X will give me a Y and a C given some configuration. Okay, so here's my combine. We got A and X, and now I can just go do. So keep in mind here, this is the function instance for monad, so I can actually go do and then just say, okay, apply F to A and get back the B. Note that I didn't pass the config into F, and here I apply G to X and I get back my Y, and here I apply H to B and I get back my C, and now I can pure Y, C. So what I've done here is write a function that takes in a parameter config, but I never actually mentioned that I did, right? And I, instead of calling the functions directly, I use the do notation to call them, and I use the left arrow to call them, and it implicitly will pass this configuration in to each of these functions that need it. So this is called the reader monad. It's quite a useful situation whenever you have a program that requires some implicit configuration or state to be passed in, but it doesn't modify that. It's just like a static bit of data that you need to pass into all of your functions. You can use the reader monad to do that. And it can be a bit nicer than manually passing in config to every single one of these functions. So that's what the instance for functions is used for. And similarly, we can, using a monoid instance for writer or for the tuples, implement a monad for X. And this is essentially the same thing as what we did for applicative. And this is used for keeping logs, basically, or returning an additional value and hiding that extra return value. So just like reader hides an additional input, writer hides an additional output. And in the Haskell standard library, both functions and tuples are used as monads for these purposes. Generator is also a monad, and we will we will do an example later which demonstrates that. And IO and state obviously are monads because you were using them as monads last week. So what are the laws that monads need to satisfy? So we have, let's just define the special composition operator for functions. It's essentially the type of the composition operator, B to C, A to B, A to C, right? It's the same as composition, except each of these functions returns an M of C or M of B, where M is a monad, right? So this is a function composition operator, and I implement it using bind by just basically apply X to G and then bind the result into F, right? And the laws for monads are much more easily expressed using this function, this composition operator, rather than this bind function. So the way they look is as follows. So it just looks like the monoid laws, not monad, sorry, monoid. We have, if you have f composed with g composed with x, that's the same as f composed with g composed with x, associativity. Pure composed with f on either side is just the same as f. So this is like the monoid laws, except we can have multiple different types here. So we could have pure, like f can go from a to b, right? And this can go from b to c and c to d and so on. So they actually go from different types to different types, which means that it's not quite a monoid, because monoids are expected to always be the same type. This sort of structure is called a category. So if you've heard of category theory, that's what deals with these kinds of structures. So monads are essentially just this type class that obeys these laws. There's nothing special about them, but for some reason, everyone who tries to learn about monads in Haskell tries to write a tutorial about monads in Haskell, and they always end up confusing the issue even further. So there's a very, very nice tutorial called You Could Have Invented Monads that I will link to from the course website, that will provide a bit more insight onto monads, and also the relevant chapters in various Haskell textbooks will be useful. However, yes, once you understand what's going on here, please, please, please restrain your impulse to write a tutorial. There are already enough bad tutorials about monads on the internet, and you will probably easily be able to find some if you Google. So be careful about what you read on the internet. A lot of people say wrong things or wrong intuitions. Even famous people, if anyone's heard of Douglas Crockford, do not listen to what anything he has to say about monads, because it's all rubbish. So be careful about clueless people pretending that they know what they're talking about. You can always ask us if you're having trouble, of course, and we'll help you out. So, how does monad relate to applicative? Well, we can, or as we demonstrated, we can always implement star using the applicative, using the monad instance. I did it in do notation in my code, but in the slides here we just used the raw bind function and lambdas and such, which is very unpleasant, but it works. And this implementation is called app. Like, so the word app, AP, is provided in the Haskell standard library, so we can, if we ever want to define a monad instance and then define the applicative instance rather than the other way around, which is how Haskell normally expects it to be done, we can just define star using app and then define bind ourselves, right? And as we've seen before, we can use do notation to make this a bit easier. So instead of using the bind function applied to a lambda, we can just change, we can go do x bind, this the left arrow can also be pronounced bind y, and then do z. And bind and ignore the argument, or use the double arrow function without the equals, its equivalent, is just x and then y in the do block. So you've seen examples of this already, I'm sure. Okay, so now we're going to do a few examples. So let's do some dice rolling. So the first problem is we're going to roll two 6-sided die, and if the difference is less than 2 of the two numbers, then we'll re-roll the second one, and the final score is the difference of the two. Okay? So, firstly, I'm going to use an I/O procedure to do this, because you've seen I/O before, and then I'm going to use a different type of monad to do something else. So, first we want to have a function that will roll a dice, or an I/O procedure in this case, that's going to roll a dice that returns an integer. And I'm going to use random RIO. Let me check, actually. I think it's like this, so we'd say we want it to be from 1 to 6. I need to import system.random. Does that give me 6 as well? Yes. Okay, so it seems to be inclusive. Just double checking that. So let's write our implementation of this silly dice game. Essentially what we do is first we roll the dice 1, and then we roll dice 2, and if the difference, the absolute value of d1 minus d2, is less than 2, then we will roll dice 2 again and return the final score, which is the absolute value of d1 minus d2 prime. Otherwise, we will we will just return the score as is. Okay, so this is our dice game. Very simple. So we can try playing this game and seeing what happens. So if I go, my score seems to be very frequently 2, but I am getting some other scores sometimes. So now what I'm going to do is change which monad I'm using, and the only thing that will change here is the roll function. So I'm going to change it now from an IO procedure that randomly returns an integer to a list of all of the possible return values of or all of the possible dice values that I could get. Now, what does the list monad do? Well, it's going to essentially you can think of it as doing is concat map, right? So it's going to take, for each element of roll, it's going to run the rest of this computation. So for each possible D1, it's going to run the rest of this computation and concatenate all the possible results together. So then it's going to be for each D1 and for each D2, it's going to calculate the possible results, and then for each D2 prime, all of the possible results, and concatenate all of them together. So what this will do, if I run this now, I didn't change the dice game at all I did is change roll. It now gives me all of the possible scores that I can possibly get. So I used this to basically simulate non-determinism. We can make many choices and it will try all of them, right? It allows us to exhaustively go through an entire set of possibilities. So this is equivalent to what's called a list comprehension. In fact, Haskell has list comprehension notation. We've never used it in this course, but it is commonly shown in Haskell textbooks and so on. And list comprehensions also exist in Python and several other languages. And this do notation is actually very much like a list comprehension now. We are saying for every D1 in roll, right? So for every one of these, and for every one of the D2s, return, for every D2 prime, the difference in these scores, or the difference in these scores if the difference is less than 2, right? Is not less than 2. So the dice game here is essentially a convoluted list comprehension. And now we can answer the question that's on the slide. What is the most common? I need to import data.list by going sort dice game. And what am I doing? It's not bash. Okay. And now we can find out. We just go map length. It looks like 2 is indeed the most common score that you can get from this game, because it's 30. It appears 30 times in this tree of possibilities. Cool. Okay. So here we have, let's suppose we have a database of student IDs and mapping them to names. So let's go back to our code. If I have my database is a list mapping ZID to name, and it's going to take in, so okay, we have me. So it's just a list containing tuples. And then we have Rich. And then we have Mort. Okay. So these three characters will be our students here. And now we want to write a function that like I don't know, gather students, student names, that given a list of ZIDs returns maybe a list of names only if all of the student names or the student ZIDs could be found. So student names given an empty list is just going to be pure of an empty list, right? Student names of a single element would be, let's say I have a ZID here. First, I need to look up Z in the database, and that's going to return maybe of the name if it exists, and nothing if it's just if it exists and nothing otherwise. And then, so I'm going to use do notation for this. First, look up the name, right? And then look up the rest of the names. So I'll use student names, recurse, go down into the rest of the ZIDs in my database, and then once I'm done, put it together with pure n ends. Now, we can see here that there's no dependency on student name Zs and lookup ZDB, right? So these two expressions here are independent. This is a sign that we can actually use applicative here instead of monad. This is equivalent to writing. We can write it this way, and of course there's nothing stopping you, and by all means do it if you wish. But you can also write this more neatly, I think, as cons fmap lookup ZDB star student names Zs. So what's going on here? Well, student name Zs is our list of is our maybe of the rest of the student names, and this is lookup ZDB is our maybe of the current student name, and we just try to apply cons to those two arguments, assuming they're both just. And if either of them are nothing, we return nothing. It's the same thing as what's happening with the do notation here. Okay. The last example is a tree type. So we're going to define a quick check generator here for trees. So I'll just comment this bit out. First, we need to define a tree. So let's have tree of A is a leaf or a branch of A and tree of A and tree of A. And let's derive show and EQ for good measure. And now I need to write a generator. So we'll make it an instance of arbitrary for good measure, tree of A, assuming we can generate A's arbitrarily, right? And let's write our instance. So we have an arbitrary. First, we need to decide, are we going to use generate a leaf or generate a branch? Now there's this nice tool here actually called frequency, and we'll have it with a frequency of about 0.1. Oh wait, we have to use whole numbers. frequency of 1, it will just generate a leaf. So frequency, if I show you the documentation, let me just get some space to do that. Okay. So we have frequency is given a list of numbers and generators. It will produce a generator that will choose one of these generators to run with the given probability. Like it weights the distribution. One of is the same except the distribution is even. So I want to weight it because I don't want leaves to be too common. I want it to have other things than just empty trees all the time. So about twice as often we will have branches, and I'll write that as a separate generator. So branch is going to be, actually, you know what? I'm going to do this differently. I'm going to say search trees. What we want to do is generate an arbitrary search tree, not just a binary tree in general. So what we want to do is first have a minimum and a maximum. So we'll get our min is going to be an arbitrary integer, and I'll just make it clear by writing a type signature for it. And our maximum is an arbitrary integer. And well, I want the minimum to be greater, or the maximum to be greater than the minimum. So what I'll actually do, this is the delta, and let maximum be minimum plus delta, and I will make sure that it is positive, right? So I'm using some of the quick check modifiers here to ensure that I generate a positive delta. And you can do pattern matching on the left-hand side of a bind like this, it's fine. So now I have my minimum and my maximum, and I'm going to generate a search tree with that minimum and that maximum value. So my search tree function is given a minimum and a maximum, return a search tree, or a generator of search trees. Let's just say arbitrary of tree of int, because I'm generating arbitrary integers here. Okay, so now search tree, minimum, maximum. If the minimum is greater or equal to the maximum, then we will actually, let's go with greater than the maximum. Then we will just return leaf. Otherwise, I want to return let's do a branch, and we'll pick a x. So firstly, what we want to do is pick an element that lies in the range. Is there one for ranges? I believe there is. Choose. Right, so we can go choose between minimum and maximum, and that will be a generator of integers. So we get our value. And then we want to generate the left subtree, which is a recursive called search tree, where we pick the minimum is still the minimum, and the maximum is now v. And the right subtree is search tree, where the minimum is now v plus 1, and the maximum is now mx. And now we just return the branch containing the value, the left subtree, and the right subtree. So here I'm using monad code to sequence all of these generations together and produce a generator for branches. Okay, I think that'll work. I haven't tested this, so I need to import test.quickcheck. I need flexible instances, That's just because I made an instance specifically for tree int. This is a very common language extension that I think will be standardized in the next version of Haskell. So it may not be necessary to do this in the future. Okay, I've made some typos. Search tree doesn't take a tuple, it just takes 2 arguments. So I need to fix that. Choose threw me off. Okay, so now if I use the sample function from QuickCheck, it sample, like for example, if I ask for an arbitrary integers, it just gives me a bunch of examples. So if I use sample for my arbitrary tree of integers, why doesn't it like that? Oh, I need my gen here. I forgot to put that in my type signature. Ooh, okay, looks like I've made a mistake because we're getting infinite size trees here. I think this needs to be greater than or equal to. There we go. So now we're getting a whole pile of different trees. And they all should satisfy the binary search property. Looks like they do. Cool. Okay. While we're here, we can also test my student names function. If I provide a bunch of ZIDs that I know exist, it will give me both of the names that I wanted. But if I make a mistake, it will say nothing, right? Cool. So those are the examples that I wanted to show you. Before I wrap up this lecture, there's another example of a monad instance that's quite useful. It's for the type either. So we haven't actually seen either before, but it's very, very straightforward. It has 2 constructors, left and right. One is for the left-hand side and one is for the right-hand side. And either is very similar to maybe in that left is often used to represent an error and right means I successfully return. So left is kind of like nothing and right is kind of like just. And the monad instance works that way too. So if any of the functions in which you're composing with monad or applicative return left, then it will immediately stop, return left, and that error message. So this allows you to associate error messages with a failure. So you notice here in my student names, I have if it can't find a particular student, then it will just crash. Well, it won't crash, rather. It will just return nothing, which isn't very informative. But if I said either, it will give me the failing ZID. Oops, no, this is the wrong one. Down here, I meant. If I change this to be either, it will give me the failing ZID, or it will give me the student name in question. Then everything stays the same, except for lookup, because lookup returns a maybe. So what we'll do is we'll say case of, and there's a function in the standard library to do this, but I'm going to do it explicitly. If it's just, I return right, and if it's nothing, then I return left, and I will give it as the ZID that I tried to look up, right? So now my function still loads, but if I put in the right student numbers, it gives me the right answer. And if I put in a mistake, it will say, I couldn't find one for this particular element, right? And if I have another one that is still there afterwards, it will say, no, I stopped as soon as I found this one that I couldn't find. And now it works again, right? When I fix it. So either is essentially the left-hand side or the right-hand side, but in the case of the monad and applicative instances, it's biased towards the right-hand side. If the right-hand side is treated as successful and the left-hand side means failure. And so when you have a failure, it will immediately abort the computation, right? It's quite useful for error handling, and it's one of the most common error handling mechanisms in Haskell programming. Okay, I think that's all I want to show you today. I think we've gone through more than enough stuff. I know this is a little bit tricky to get your head around. Feel free to, bash your head against it for quite a while. It can take a little while to sink in. We'll give you a bit more practice with this week's exercise, as well as the next assignment, which will come out the week after this one. I believe we'll be covering everything you need to know in week 8. And then you'll be able to get some more practice with Monads. So hopefully Monads will become familiar enough to you by the end of this course. They are very useful. They come up very often, even in languages that aren't Haskell. And once you know them, you'll be able to spot them showing up in all sorts of applications and use cases. So don't be disheartened if it takes a little while to understand. That's okay. Just keep working at it and keep trying to get a feel for programming with it. The easiest way to get a good understanding of these is to just program with them for a while, and you'll get a sort of an understanding of what's going on. Hopefully that's already begun with last week's exercise. Okay, thank you very much. Oh, and as usual, make sure you do your quizzes, and the new exercise is already out, so take a look at that, please. Thank you.